Okay, so welcome. So this is the first in a series of lectures on string theory. These lectures will go on at least till next year, but depending on various things, including your interest in the course, we might continue the subsequent semesters. Okay, so it might be a year and a half long. The plan for the first part of the course, by first part I mean till May, is to go through a treatment of perturbative string theory. Okay, so the main textbook, the textbook that will be most useful in this course is Polchinski. Polchinski has written a couple of really nice textbooks in string theory. We will follow Polchinski's book, mainly chapters 1 to 4, through large parts. And this will be the most useful single reference. Other useful references are the book by Green, Schwartz and Ricky. And another book that I found useful by learning string theory was a book by Lust and Tyson. Through the course, we'll also follow other references, but I'll tell you about them as we get to them. Okay, so as far as books go, these will be the main references for our course. Okay. Good. So any organizational questions or comments before we start? So the plan is to have the classes on Tuesdays and Wednesdays, same time, 2:30. Okay, great.
This Friday is no class or?
This Friday we could take a call on that. How about having it this Friday and then from next week till Tuesday and Wednesday? So we have 2 classes. Okay, good. So what are we going to do? Well, so let me give you 5 minutes, a 5-minute spiel on why we're studying string theory. Okay. As all of you know, quantum theories of 3 of the 4 basic forces of nature have been successfully developed, successfully tested in accelerator experiments, and work very well. Okay. These quantum theories are quantum theory of electrodynamics and the gauge theories that govern weak and strong forces, the SU2 and SU3 gauge theories. Okay. These theories are based on a classical Lagrangian, but we've understood how to do quantum mechanics with these theories by quantizing this. Okay. Now, well before we got understanding of, for instance, the classical Lagrangians of the weak and strong force, we had good control over the classical action for gravity. The Einstein action was written down in the early part of the last century, many years before strong forces and weak forces were even begun to be used. And we have very good understanding of the classical physics of gravitation. In some limits, Newtonian physics; in more extreme limits, it's given by Einstein's theory of gravity. These are very well understood theories, and we understand them in very intuitive and very nice ways very well. Okay. However, as all of you know, the way that electrodynamics developed, first Maxwell wrote down his classical theory of electrodynamics that was written in nicer ways later time, and then various people starting from Dirac and then Feynman, Schwinger, Tokunaga, and various other people understood how to convert that into quantum theory by quantizing the Lagrangian. Okay, so it's natural. A natural course of events would have been that somebody smart would have taken the Einstein Lagrangian and quantized it. Okay, that has never successfully yet been done. That program of taking the Einstein Lagrangian and trying to make a quantum mechanical theory based on it, just by following the usual procedures of canonical quantization, that some of you know and others of you will study when you study quantum field theory, has never successfully been achieved. Okay, there are various technical reasons for this achievement, for this lack of which we won't try to go into at the moment. Okay? But though many people have tried, it has never this program has never successfully worked. Okay. Now, what is the lesson from that? Well, of course, one possibility is that we haven't been smart enough. The right, young, brilliant guy will come and explain how to make a quantum theory that has the Einstein Lagrangian as its classical limit, and then we're already happy. At least we have a quantum theory of gravity. However, the program of trying to quantize gravity has proved so hard, has left so little insight. All the attempts have tried. Okay, yeah, in my opinion, not led to any, very much. So you might think that there is another possibility here, and that other possibility is as follows: there is no such thing. Well, that it's just misguided effort to try to make a quantum theory of gravity by quantizing the gravity Lagrangian. Okay, a consistent quantum theory, and an analog would be something like this. In the study of the weak interactions, there was a phenomenological stage in the study of that theory, in which people realized that many experimental results could be obtained using 4 Fermi interactions. Okay. Now, if you try to write down a Lagrangian, so some action which has 4 fermions, the detailed contraction structure doesn't matter, sign of 4, and you try to make a quantum theory based on this Lagrangian, you run into various troubles. 3. Some of them are analogous to the troubles you run into when trying to study gravity, or trying to quantize gravity. And the way we understood how to make a quantum theory of this interaction was not by correctly quantizing the Lagrangian, but by realizing that there were more degrees of freedom than just the fermions. There were, in addition, the W bosons of the weak interactions. Integrating out the W bosons in some approximate regime gives you the theory of 4 Fermi, this 4 Fermi interactions. But the theory that we know how to make sense of, the theory that is so well tested in accelerated experiments, is a theory with fermions interacting with W bosons. This is not part of the basic interaction of the theory, just a phenomenological effect of interaction that you integrate out some things. So, in that case, the lesson was that we should try to make a quantum theory based on this action. We should instead look at a larger system, which you can understand and make consistent, and when you take the appropriate limit of that larger system, it recovers the physics of this phenomenological model. Okay? So there's a second possibility that at least most consistent quantum theories of gravity, perhaps there's some, well, okay, we get to that at the end of this course, but that at least most consistent quantum theories of gravity should be thought of as larger systems with degrees of freedom that go beyond the graviton, but that for some reason, when you go to appropriate limits, the appropriate limits will be low energies. Okay, reduces to the physics of gravity. So this is the second possibility in the game. Okay, now string theory is an attempt. Is a formalism that implements possibility number 2. Okay, it is a consistent, as far as we can tell, consistent quantum theory that has many more degrees of freedom than just the graviton. Okay, but that at low energies reduces to a theory of gravitons interacting with some small amount of power matter. Okay, within the string theory, it seems clear, all of the statements that I'm making are statements that at various points in the history of the development of the field have been challenged. Some of these challenges have come very recently, 2-3 months ago. So everything I'm saying is based on current understanding, which may turn out to be wrong next week from all this in. But as far as we understand, if we look at string theory and we take the low energy effective action, the action of gravitons interacting with the other stuff, there is no sense in which you can make a consistent quantum theory just out of those fields. You need all the fields of string theory to make it all work. Yet, the effective dynamics at low enough energies is that of gravity. Okay? So this is the program that string theory implements. Okay? And it's the program that we're going to study in this course. Okay. Now, one or two comments, one or two more is just placement comments before we start the technical stuff. The first thing I want to emphasize is that string theory, as you will see as we go along, is in some sense badly named. Firstly, the string part of that name is not entirely accurate. Secondly, the theory part of the name is not entirely accurate. You know, strings happen to be just some of the excitations within this theory that we build. Okay? But also, the statement that it's a theory is a little inaccurate, in my opinion. Especially, you know, from the point of view of the experimentalist, string theory is more of formalism than a theory. Okay. As we will see, string theory, we build it out as a theory, but it will turn out to have many, many different vacuum states. The physics about each of these vacuum states will be inequivalent. You know, a low energy observer sitting in one of these different vacuum states will see completely different physics. Where you are in the space of vacua, from the point of view of a low energy experimenter, is like parameters. So what string theory will turn out to do is to build a whole class of different low energy theories. Okay? So in some sense, can be thought of, in my opinion, in fact be more accurately thought of as a formalism rather than a theory. Okay? So it's a formalism within which it will prove possible to build consistent quantum theories of gravity. Okay? And we're going to study this formalism in this course. The second thing I want to say immediately is that, as I've already alluded to, it will turn out that the string formalism will be able to build thousands, an infinite number of consistent quantum theories of gravity. Okay? So in that sense, string theories of formalism, it's like quantum field theory. You can't ask, what is the predict? Does quantum field theory reproduce the hydrogen atom? That statement makes no sense because quantum field theory is formalism. A particular quantum field theory does reproduce the hydrogen, the physics of the hydrogen. Okay? In the same sense, string theory, at least in my current understanding of the subject, in my opinion, is formalism. And the question, which is of deep interest to all of us, but does string theory explain the real world, is as imposed as the question of does quantum field theory reproduce the spectrum of the hydrogen atom? You can't, string theory by itself can't reproduce the real world. It's a particular implementation of string theory, a particular theory within the string formalism that may or may not be the theory of the real world. Okay? Now, all of us who study string theory hope that that's the case. But we have none at all, no experimental evidence, no terribly pressing reason yet to believe, no overwhelming reason yet to believe that is true. Okay? So string theory is a formalism. What it has, its successes so far have been that it has been a consistent formalism within which it has proved possible to make consistent quantum theories of gravity, a whole zoo of quantum theories of gravity, and in my opinion, it's the only successful attempts by human beings to make successful quantum theories of gravity. But once again, by quantum theory of gravity, what I mean is theory that is consistent and quantum mechanical, and that low energies is effectively described by gravity. I don't mean something that implements quantization of the line standard equation. Okay? So, all the successes, and we'll see many of them as we study this course, all the many interesting things that emerge in the study of string theory, all the successes have been formal successes. They have been successes about relating one formalism, like gauge theory, to another formalism, like gravity, and understanding wonderful things about these various formalisms. But string theory has had no concrete success yet in implementing the theory of the real world. So which vacuum string theory, if any, is the theory of the real world? It's unknown, completely unknown. Okay? And there is no overwhelming experimental reason to believe that any of these is the theory of the real world. Okay? So string theory has been successful as formalism for quantum gravity. It is also an attempt at phenomenology. And formalism within which phenomenology can be placed. It's the only, in my opinion, the only formalism that we know of within which you can try to make the theory of the real world, because it's the only formalism that has both quantum mechanics and gravity. Okay? But it has had no concrete success yet in reproducing the real world. So you should not think that all of the calculations we're doing are calculations about the theory of the real world yet. We don't know that that's true. Okay, so these are the general placement remarks I wanted to make about string theory. Any questions or comments before we continue to technical analysis? Please.
What sort of a background would you recommend coming into this course?
Okay, so the things that will be essential are an understanding of quantum mechanics. A very good understanding of quantum mechanics. That is what will be essential. Okay, things that will be useful is exposure to the general theory of relativity and exposure to quantum field theory. Okay? Neither of these will be totally essential, but they will be useful. Good. Other questions or comments? Fantastic. Okay, so let's start. So, in the next 20 lectures or so, what we're going to try to do is to undertake a quantized. Okay, so one more situation remark about stuff. Okay, as you will see, the basic idea of string theory is that the various particles that make up the real world, well, this is an inroad into string theory, come by quantizing the motion of a little string. Just like quantum field theory can be thought of as arising from quantizing the motion of particles. Okay? So, the next several lectures, at least 20 or so, will occupy us with the process of consistent quantizations of strings moving around in space-time. Okay? But before we get to that, let's back up a little bit and ask how we can quantize the motion of a bosonic relativistic particle moving in flat space. Okay? So our situation is R, let's say, d minus 1, 1, by which I mean we're in flat space with d minus 1 spatial dimensions at one time. And I want to understand how to quantize the motion of a relativistic particle moving around in this vacuum. Now, so in order to do that, what I want to do is to write down an action. So S is equal to something. Okay, but even before I talk about the action, I have to talk about the variables. What are variables? Okay, now all of you know how to think about this, because this is the kind of question you ask in quantum mechanics. Understand? The variables of the problem are the position of the particle. It's a bosonic scalar particle with no internal difference of frequency. So the position of the particle, let's call it xi of t, is the standard set of variables that you use in trying to make quantum mechanics. However, in using these variables, you break manifest Lorentzian variables because you choose variables to be space and t to be a parameter. Lorentzian variables mixes space and time coordinates, so this doesn't look like the kind of thing you want to do if you want to preserve manifest relativistic invariance. Okay? So unmotivated as it may sound at the beginning, okay, let us start by trying to make a formalism in which the variables are not xi of t, but x mu, where mu runs over all spatial as well as the time coordinate, as a function of tau. Now immediately you should ask me, what the hell is tau? Okay, there is nothing else in the problem, the space and time. So tau is a fictional parameter. And as soon as we set up the problem in this way, we must make sure that we set it up in a way that is independent of what tau is. Okay? So any action we write down for these variables, any action we write down for these variables has to have the property that it is invariant under the following transformation. Tau is equal to f of tau prime. By which I mean the action function written as a function of x of tau prime should take the same functional form as the action function written as a function of x of tau. Okay? Because there's no tau is going to be some parameter that tells you where, parameterizes the path of particles, some arbitrary parameter, let's say starts from 0 and goes to 1 in some given process. There's nothing physical or invariant about it, so we should be able to change parameterization at will without changing physics. Is this clear? Okay, so that's going to be our guiding principle. How do we write down an action? That's going to be our guiding principle. So let me try to write down one action that has this property. Okay, now an action. So once again, tau is some arbitrary parameter that parameterizes world lines. We want to write down an action for x mu of tau. Now, how do we write down an action that does not depend on what tau is? A simple way to do that is to make our action a geometric quantity. Okay? In order to understand this, let me give you the example that will turn out to be what we want. Let's choose the geometric quantity of length. So suppose I have some path parameterized by tau, let me write down an expression for the length of that path. Okay? So the length of the path, let's say for a moment, so we're working in Euclidean space, we get a minus sign right in Cousin space. But if we were working in Euclidean space, well, we know that if there are 2 points and the difference between the coordinates of these 2 points is dx mu, then the length between these 2 points is simply dx mu to dx mu. Square root. The metric is 1. The identity. Okay? Now x is parameterized by tau. So what we could do is put a d tau here and put a d tau there. But we don't really want the tau. That's just fictional. It's fake. So we multiply and divide by d tau, so we put a d tau. Okay? This object is an expression. Now I include the integration sign. So this object is an expression for the length of the path. Traversed by this particle, and is clearly independent of rescaling of redefinitions of the variable tau, because you can write it without a tau. Is this clear? So first exercise. Okay, I want you guys to satisfy yourself as clearly as possible that if I write if tau is equal to f of tau prime, okay, you make this change of variables, rewrite this action as a function of tau prime. You get the same. You get the same expression as a function of tau prime. It's obvious. It's obvious we've done it, but I want you to convince yourself. Okay. So this action expresses geometric quantity. The parameters are fake. So it has a property that we want. Okay. Now let's move to Euclidean space, to Minkowski space. Okay, and write down the action that will actually be of interest.
This is any transformation, so it does not singular Jacobian, right? I mean,
yes. You will have it. That's right. You will have.
It should not be multivariate.
That's correct. So Suresh's comment is a good one. The transformation will have to have the property that tau is equal to f of tau prime is a one-to-one function. It doesn't go back. That's true. You see, basically, the point is that suppose you take Suppose you take this following path, and then you choose a parameterization that does this. Then that changes the length of the path. You see, along this parameterization, you're not computing the length of the path. You're computing the length of the line that you're traversing, which is larger than the length of the path. Okay? So you want one honest variable that really parameterizes the path. Okay? And then all variable changes that will be allowed will be honest variables or changes of that honest variable, namely one-to-one variable changes. Good point, thank you. Okay, good. You'll see that that's needed because there's a square root here which will bring out an absolute value. If you try to do this exercise, you'll have an absolute value here that will have to cancel with a number there. So that absolute value, that's how. But we'll read the expression. Okay, good. So now let's move to Minkowski space. So we want to do the same thing for Minkowski space, except we were interested in paths that are time-like, because that's how particles move. Okay, so in our metric conventions, let me immediately set up a metric convention. Our metric convention will be minus plus. So time-like vectors have negative length. Okay, so in our metric convention, we need to include a minus sign inside the square root in order to be taking the square root of a positive quantity. Okay, So now metric convention, S is equal to minus of dx mu by d tau, dx mu by d tau. And now we can put any constant we want behind this action, that doesn't change anything. It will turn out to be useful to have a negative constant, as we will see in a moment. Okay, so this is the action that we're going to start. The action for the motion of a relativistic particle, relativistic scalar particle. Okay, good. And of course, this is the down here. Okay, is this clear? Any questions, comments, or any discussion about what this action is? Okay, good. So now see. Before we go on to the quantization of this action, let me first convince you of something you're very familiar with. Okay? So, one of the things we said was that the parametrization of the path should be faithful. That is, any given value of the parameter should correspond to a single point of the path. Okay, now, if the particle always undergoes time-like trajectories, classically that's what we're going to do. So, if the particle always undergoes time-like trajectories, then there's one obvious parametrization of the path, namely the time. Okay, so we could use any parametrization for tau. Let's choose for a minute to use time. Okay, so what do we get? Then dx0 by d tau is 1, but when we contract that with metric, it becomes minus 1, which cancels this side. So S is equal to minus m integral of 1 minus vi squared, where vi is okay? Now, several of you identify this and have studied already the motion of relativistic particles and know this is the famous action for the motion of a relativistic particle of mass m, which is, for those of you who haven't, let's check that at least reproduces the correct non-relativistic limit. In order to do that, of course, all through this course, the speed of light is 1, h cross is 1. Okay? We'll reinstate it with great difficulty if we need these things. So v is b units of speed of light. Okay, so let's see if we get the right non-relativistic limit. Let's expand out the square root. Once we expand out the square root, we get minus m plus mv squared by 2 plus higher orders. Minus m is a constant, it doesn't affect physics. Mv squared by 2 is the correct non-relativistic Lagrangian. Okay, so we've started with a Lagrangian that at least was guaranteed to have the right non-relativistic limit, and in fact, is the famous Lagrangian for the motion of a relativistic particle. Okay, good. So the starting point makes physical sense, even though it looks pretty formal. Questions, comments about this? Okay, great. So I should have said that because this course has been videotaped, I'm not allowed to stray beyond this line and this line. If somebody catches me doing that, please push me back. Good. Now that we've agreed that we've got a good Lagrangian, we're going to try to quantize it. Okay, how do we do that? Well, let's just implement the standard procedures of canonical quantization. So what are standard procedures of canonical quantization? The first thing we do is to write down this action in canonical terms. The first thing we do is to compute the canonical momentum. The canonical momentum P mu, which is del L by del X mu dot. Okay, so what's that with Lagrangian? Well, what do we get? So there's we get m by square root of minus x mu dot x mu dot. So dot is going to denote derivatives. Tau times x mu dot. The two minus signs are cancelled. Okay, now that we have the canonical momenta, you might think that in order to make quantum mechanics, all we have to do is to replace canonical momenta by derivative operators. Okay, and coordinates by the x, the coordinate operator, and with root. However, things are not quite so simple. We know that this shouldn't be so simple, because if that were true, then the answer to quantum mechanics would be a Hilbert space of functions of d variables. Whereas in the non-relativistic limit, we know that the right answer is Hilbert space of function of d minus 1 variables. We've got the wrong number of variables in the problem. So things shouldn't be so simple. We should see that somehow. How do we see that? We see that from the following way. You see, you look at the momentum here, and then construct the following object. Construct P mu P. Okay, so what do we get? What do we get? We get m squared x mu dot divided by square root of minus x dot mu. Okay? So this thing is minus m squared into sorry?
Square root is not there.
It was not there
In the denominator, it won't be there.
Oh, thank you. Lovely. So we just get minus m squared. And therefore, we say that P mu plus m squared is equal to 0. Okay. Now, what have we found? You see, from the formal point of view, P mu's were canonical momenta of our action. They label points in phase space. Points in phase space give you all allowed initial conditions of classical mechanics. This equation is telling you that not every assignment of momenta is an allowed state in your theory. The momenta have to lie on a specified surface. People who study these canonical quantization with such relations between, in the standard implementations of canonical quantization, x mu's and p mu's are completely independent variables. There are no relations between them. Okay? We run into a system in which that's not true. The momenta are constrained to obey such an equation. Okay. So how do we implement the quantization of such a system? Now there's deep general theory developed by Dirac to study the quantization of canonical systems, and I really read that there's a little book he's written on lecture notes in quantum mechanics, Yerisha, something like that, lecture notes in quantum mechanics, which is a real pleasure to read. So if any of you is interested, I really strongly recommend that book to you. But we're not going to go into some deep theory, we're just going to follow randomness. Okay. So how do we do the implementation of the system? Well, actually, something else we should do before. Okay, so we'll notice that we've got this constraint. But okay, let's ignore that and proceed for a moment. The next thing we do is to compute the Hamiltonian of the system. So we want to compute the Hamiltonian. Fine. So the Hamiltonian of the system is P mu x mu dot minus m. Can anyone quickly do the algebra and see what this gives us? Good. It's 0. Can you see why? Can somebody give me a reason for that being 0? Very good. Hamiltonian generates shifts in tau, but tau is a fake variable. So shifts in tau should do nothing. At a more mathematically technical level, you see, the Lagrangian itself, was a homogeneous function of degree 1 in derivatives. Okay? Therefore, this quantity is guaranteed to be the Lagrangian once again. Right? Because for any homogeneous function, you add the derivative of a variable times variable on that function, you get degree times the function. Okay? So, this was guaranteed to be 0. So, you see, we run the system with two odd properties. Firstly, the Hamiltonian just vanishes. Secondly, the system has constraints. These two properties, of course, are related. Okay. Now, if you were a master of Dirac's techniques of quantization, you would understand that his prescription for dealing with this system would be the following intuitive prescription, which I'm just going to tell you everything. The following intuitive prescription which says, go ahead and quantize your theory, ignoring the constraint, but implement the constraint as an operator equation that physical states have to satisfy. Okay? This is a so-called first-class constraint. I'm not even going to explain what that means. And this is the general procedure for quantizing systems. First-class constraint. Okay, you don't have to know the general theory. It's some formal outcome. You know, as always, what we're doing when we have a classical theory and you're trying to make quantum mechanical theory is to make any quantum mechanical theory that is consistent and has the right classical limit. So if you find a procedure that works, it's as good as anyone else's procedure, no matter how fancy his name is. Okay, so that's what we're going to do. We're trying to find a procedure that works. Okay. So I'm clearing this set. So let's see. Okay, so so firstly, suppose we just did the quantization. So what's the answer to the Hilbert space? The answer to the Hilbert space is functions of x mu, with the norm we'll discuss in a moment. Okay, the answer to the Hilbert space is functions of x mu. Okay, but you might say, well, hold on. In ordinary quantum mechanics, we have functions of our variables and also time. In this case, should we say functions of x mu and tau? The answer is no, because the Hamiltonian is 0. So Hamiltonian is what changes the state as you move in time. The state doesn't change, so it's not a function of time, it's just a function of x. So this is our Hilbert space. A normalizable function with a given norm, which we'll discuss in a moment. Okay? Now, not all wave functions of this form are physical. Only those that satisfy this constraint. What does it mean for a wave function to satisfy the constraint? Well, we know p mu is equal to minus I del mu. I almost wrote an H cross there, which would be a cardinal error. Okay? So it's minus I del mu. So let's put that in. So the constraint that we have is psi of x mu acted on by minus I squares to minus 1 del mu plus x squared and psi of x is equal to 0. Okay? Now, what sense is this making? In order to see what sense this is making, let's try to go back and use a much more lowbrow approach to the quantization of the system. Let's go back to the Lagrangian. S was equal to minus m square root of 1 minus di squared. Xi dot squared. Where we chose a particular implementation of what tau is. Okay? How do we do the quantization of this system? Well, if we did the quantization of this system, we would have the variables are just xi. Okay? So what is pi? Pi is equal to mxi dot divided by square root of 1 minus xi dot squared. And the Hamiltonian is equal to, well, we can compute it, but you know what the answer is going to be. It will be pi squared plus x squared. When you do the algebra, it's something you're all familiar with. Now, if we were to work out the quantum mechanics of this system, what we would have is the wave. Oops, this is not good. So what we would have is the Hilbert space is a function of square integrable functions of xi, but the Hamiltonian is not 0. So it's also a function of time, and it's not. And this wave function obeys the Schrodinger equation. What is the Schrodinger equation? The Schrodinger equation is minus I d by dt, plus the I d by plus I d by dt on psi is equal to h of psi. H is this. So that's minus del I squared plus m squared on psi. Now let's take this equation and square it. Act on it with I d by dt again on the left hand side. Use the factors. Then we square the operator. So what do we get? We get minus d by dt squared psi is equal to minus del I squared plus m squared on psi. Okay, which is the same thing as in our sign convention, minus plus d mu minus m squared on psi is equal to 0, which is minus the sequence. So that's right. Okay, so you see that these two methods of quantization given us the same answer. They've given us the same answer, but in different ways. You see, the constraint that came out of working with constraint in our first way of quantizing was simply the Schrodinger equation that described time evolution in the second, more physical, more crude, but more safer way of quantizing. Okay? So we've got the same answer working in both ways. And I hope this has given you a feel for what these constraints do. The problem was, you see, what was the problem? The problem was that we started with too many variables. We pretended that our variables of the system were the time of the particle as well as the position. That was not true. What the system told us was that not every state was physical. Implementing that condition gave us an equation on wave functions. That equation is what replaced the Schrodinger equation from the more physical way of quantizing. And there was no Schrodinger equation in the less physical way of quantizing because I had to do this. Is this clear? So we've got two ways of quantizing the theory. We've got two ways of quantizing the theory that give us the same result. Well, give us almost the same result so far, because I've not discussed the scalar product. Okay. Now, this is not going to be, when we do it properly in string theory, we do it really properly, so I'm just going to make a couple of throwaway comments about the scalar product, just so that you know. The wave function that we naturally get using, so let's, now that we've seen this, let's divide our board into two sections. There's physical, so S is equal to minus M, 1 minus VI squared, and then S is equal to minus M square root of minus X squared. Okay? We got a wave function and doing the quantization here. Let's give it different names. Let's say the wave function is equal to phi. I'm sorry, I called it psi here, but I'll change it. Okay, what is the natural norm for scalar products in this system? Well, we know, we've all studied quantum mechanics. There's no ambiguity. If we work in momentum space, then the norm is just, after some 2 pi's which we won't obsess about, it's a phi star of p times psi of p d minus 1 of p. This is equal to phi psi. Okay, it's just the usual thing we do, the usual measure of quantum mechanics. And what about the norm for wave functions in this way of quantizing things? You see, in that way of quantizing things, everything, the natural thing you would think about, you see, everything was a function of d variables. So you might be tempted to write, well, dp. Now I call this psi. Let's call this phi prime. Sorry. Phi's are the wave functions you get. But this one is psi is the same. Okay. You might think that the natural thing to do is to say psi star p, psi of p. Except that makes no sense, because we know that this psi satisfies the constraint that it only has non-zero support on those momenta that obey the equation p squared plus x squared equals 0. So while you can say this would just be 0. So let's enhance the contribution from that surface, and let's do it in the Lorentz invariant manner. What we do is put delta p squared plus m squared. Well,
it's going outside the...
Oh, that's right. Okay, now, this looks very nice and satisfactory. It's clearly Lorentz invariant. It's a nice norm. But I'm going to leave it as an exercise for you to check. These two norms are only the same. Only if these two wave functions are not quite equal. In fact, the conversion that works, can somebody do it in real time? Well, the conversion that works is that psi of p is equal to square root of 2p times phi. Alright, I'm going to leave this as an exercise. We'll list these exercises, by the way. So, the first exercise was to explicitly demonstrate invariance of their action. The second exercise was to check that this variable transformation equates these two norms. Okay? Having done that, you see, these are the same system. So it's the same system, but the wave function is not quite the same. Same up to a little redefinition. This was a by the way aside, which we'll understand very well when we study string theory, so don't obsess about it. Okay, good. That's all I wanted to say about these two ways of quantizing the system. Any questions or comments? Fine. So, before we turn to the quantization of string theory, I want to talk about one or two slightly. I want to kill this system to death. It's a very simple system. We know everything there is to know about it. But I want to approach the quantization of this system from many different ways, points of view, so that when you see the same kind of when we do more complicated things like quantizing a string, you will have many options in your hand and use the one that's most convenient. Okay? So, it's not that I expect to learn any new physics about a free particle. We know everything there is to know about it. But anyway, we're going to kill this problem to death. So let's continue. So, the next thing I'm going to do is to take the action, the fancy action, and make it even more fancy. Okay, so the fancy action is minus m square root of x mu dot squared minus. And, you know, while this is a perfectly legitimate action, it's a little odd and it's a little ugly because it has this horrible square root. Now, when you're dealing with something as simple as a free particle, you can deal with ugliness, okay? But when you do things that are more complicated, the ugliness will come and kill you. Okay? So, question, can you take this action and rewrite it in a way that's classically equivalent that makes it look pretty? Okay? Answer yes, and let me do it. Okay, so I'm going to have to look up the signs. Suppose you consider the following action. S is equal to m by 2. X mu dot by E minus E. And now you're going to ask me what is E, and I say, well, it's a new variable. So instead of dealing with the system with D variables, we're now dealing with the system with D plus 1 variables. Okay, we decided to I mean, if you go from D minus 1 to D, who's going to stop you from going to D plus 1? Okay, so now this looks like an odd system. So before we let us check that this system has something to do with that system. Okay, in order to do that, what we're going to do is to notice that it's very simple to solve for the equations of motion of E. Basically, because the action has no derivatives in time with respect to E. Okay, so the equation of motion are only local in tau coordinates, it can easily be solved. So let's write down the equation of motion of E. So the equation of motion for E is minus 1, that comes from differentiating this guy, minus 1 over E squared, that comes from differentiating this guy, in x mu dot is equal to 0. Okay? So that tells you that x mu dot is equal to minus of this is equal to E squared. Or E, which by convention we choose to be a positive number, is minus x mu dot. Very good. Now, right, you have to keep your wits about you with minus signs, otherwise you might think it was 0. Okay, so now let's substitute this in. Okay, so we substitute this back into the action, we have f by 2, s is equal to f by 2, and then we got this x mu dot, but we write that as minus x mu dot, and then there's divided by the square root, so this is this, and then we've got another minus square root of x mu dot, minus. So the action the system was simply equal to m minus m square root of minus x mu dot. So it's the same action. It's the same action once you've solved for E using its equation of motion as the previous system. Okay. For those of you who feel uncomfortable about working with actions once you've put in equations of motion, solutions to equations of motion, something you in such certain situations should be uncomfortable about doing, I encourage you to check that the equations of motion or that you get from these two actions are the same. Okay? E is simply determined once you know what x is. Once you plug that into the equations of motion of x, you get the same equation of motion as before. Okay? Classically, these systems are just identical. Okay? The reason we've done this ugly business by introducing a d plus 1th variable in the system with actually d minus 1 variables is that the action looks much simpler than this. Okay?
By the way, if the equation of motion for E, but it just demand that the momenta are the same for both the actions. So the momenta here is like x dot by E basically. And if you wanted to be x dot by root of x dot, then you would have, wouldn't that give the value of E?
Sorry, I didn't understand.
So you write down this action in with d plus 1 variables, demand the momentum that you get from this action for the free particle is the same as the momentum from the other action.
Yes.
Wouldn't that fix the value of E?
Good, I understand what you're saying. It's a consistency check that had to work. But it can well be that is the value of E determined by dynamics. Which we've checked. So the way I would word what you're saying is that now that we've done it, we can plug into the equation for the momentum force, and we'll find the same. Everything will be the same once you plug it.
So why should we be actually uncomfortable or plugging it back in, plugging that thing? I mean, you have increased one parameter in the space of functionals, and you're setting that, fixing that. Once you're fixing that parameter, you're reducing the number of parameters by 1.
Yeah, well, you should in general be uncomfortable about plugging solutions into an action, because you get equations of motion from an action by performing all the possible variations of that action.
Okay, but if you see that equation as a constraint, so you're again reducing all the parameters by 1, so you're going back to
right. So there's some situations in which it's correct, okay, but there are other situations in which it's not correct. Okay, there's an analogous question you could ask. Okay, it's not the same question, but it's analogous, and all of us are familiar with that. Okay, so let me remind you of that. The analogous question is, when can you plug in a gauge condition into an action? Okay, suppose you decide to work with the gauge A0 equals 0 into an action, and you plug that into the action. All the equations of motion that you will get from that action by varying with respect to AI are correct equations of motion. But you miss an equation of motion. Okay, you miss an equation of motion because there was a variation of A with respect to A0, which would give you Gauss law, which you missed. So that's the kind of thing you have to worry about. In this situation, I completely agree with you. It's correct. Fine, we should be checking it. Okay, but now let's move on. So now we want to make a quantum theory corresponding to this action. How do we do that? Well, we just follow the usual canonical procedure. We follow the usual canonical procedure, and what does that give us? Well, the first thing we say is that there's no time derivative, there's no x dot tau derivative of E. So PE is 0. Okay, what about the canonical momenta, like Shiraz? Okay, so phi mu was what? Well, we get m x mu dot by E. Okay, now the next thing we see is that if we compute okay, so this is already a constraint that a momentum conjugate to a particular variable is identically 0 is telling you it can't be an order phase space, you have to be some submap for the phase space. So you have at least one constraint in our system. Okay? And I think that you might have thought that's it. There are no other obvious constraints in the system. However, there is one more constraint in the system, which is more subtle than the initial constraint. How do we see that? In order to see that, let's compute the Hamiltonian. The Hamiltonian of our system is what? Well, the Hamiltonian of our system is x mu dot p mu minus Lagrangian. Okay, so that's going to be E times p mu by 2m plus m squared by and there's an e outside there as well by bracket. So let's get a path that's constant, just reverse the sign. And this part is exactly like the standard Lagrangian with m replaced by m by e. Okay, good. So, you remember that we had as a constraint in our system that PE was equal to 0. But this is a constraint on phase space. But now we have Hamiltonian that is not 0 in the system. So suppose we start with an object that meets this constraint. If we act on it with time variation, we act on it with the operator that generates time variation, it could leave this constraint space. That would be bad because we should demand that our particle always sits in the constraint manifold. Okay? So let's check whether it does or not. How do we check that? The way to check that is to check what the Poisson bracket of PE constraint is with Hamiltonian. But that's very simple because the only thing that it does not have 0 Poisson bracket with is E. Okay? So this Poisson bracket is proportional to P mu plus m squared. So it's not 0 unless P mu plus m squared is 0. That's the second constraint we have to impose on our system in order to have consistent dynamics. Okay, now we can check that that's it. Basically, because P mu plus m squared itself commutes with the Hamiltonian, yes. Obviously. Okay, so there's nothing else. The system is closed here. We impose these two constraints: PE is equal to 0, P mu plus m squared equal to 0. Nothing else to do. Okay, now let's make our quantum mechanics for this system. Okay, so now we make our quantum mechanics for this system. States are functions of x mu, e, and tau. However, once we impose the constraint, the Hamiltonian is 0. So states are not functions of tau. And once we impose the constraint, what's the constraint? P is equal to 0. That's d by de minus I d by de of psi of x mu e. You know, simple mention conjugate e is d by de. And therefore, the solution to this is make functions that are functionally of x mu. Imposing the second constraint now reduces this problem exactly to the one we've already solved. Okay? So, we're seeing how this works. We start with a system with d plus 1 variable, but for each additional unphysical variable that we imposed, we had an additional constraint. And that knocked it back down to the right answer when we did things carefully. Okay, questions or comments about our third way of quantizing this system? Fine. So, just to show you what varieties of quantization are possible, we're going to do a fourth way, but I promise that's it. This fourth way of doing this quantization is a poor man's quantization.
Sorry, so
please.
Is there a general rule you could extract from this? Given d variables, you want to remove r of them, just put d by dr of psi or x mu r equal to 0? That's probably what you seem to be doing here. For example, the first way, you had psi as a function of x mu comma tau, t, for example. And the constraint equation was d by dt of psi equal to 0 at the end of the day.
Right.
Now
well, that was not constraint, just the Hamiltonian.
That's right, but that was just Hamiltonian, that's right.
And the constraint then generated the true dynamics of the system. I don't think you want to make very general rules. You know, but please go. Please go. What?
No. Oh, okay, fine. But that's different from the. Oh, no, I mean, it's just something that. So you just demand, for example, that you stay on the space of constraint when you're doing time evolution.
Right.
And that gives you back the first constraint equation.
That gives you back the first constraint. Well, you see, the constraint that PE was equal to 0 was not consistent under time evolution unless it was also true that P squared plus M squared. So there's no consistent way of doing the quantization, this constraint quantization, unless you impose both constraints.
So demanding the equation of motion from both actually be the same at every instant of time, essentially. Isn't that the statement that P equal to 0 always? Because P equal to 0 is a necessary condition for both actions to be the same, I thought.
P equals 0. Well, it came out of the equations of motion.
Oh, I see. So it's not.
You see, there's nothing you put in by hand. Okay. We're doing quantization. We're following the rules. We find a constraint, and we want to impose a condition that the constraint is invariant on the time. There's nothing arbitrary here. We just follow our nose. There's the answer here. We always do things that are sensible. You land up with an answer. Basically. Okay, good. So let's do the last one. This last one is throw lines route to quantization.
In the previous way, we didn't have to bother about the fact that the Hamiltonian was identically 0 was an obvious constraint. But in this case,
well, it was not a constraint. Just told you that time evolution was true.
Yeah. But now H is not 0 identically. At least
it's not 0 identically. However, you're only dealing with states on which the Hamiltonian matches. So time evolution for physical states is true. Okay? Great. Last way. I hope we're not pushing this line further. Okay, last way. The last method of quantization uses the same action that we started with. Okay? But says, look, I don't want all this formal nonsense. Let me just follow my nose. So, the action is this. Minus plus m x mu dot by e minus e. Okay, down. 1 over. Okay. And now, I want you to notice the following. Suppose you make the substitution x of tau is equal to x prime of f of tau, and e of tau is equal to, well, prime makes it something better than called tilde. E tilde of f of tau df by dt. Okay? So I've got a set of variables, and I rewrite the action with this variable change. Okay? As exercise number 3, all these are 2-minute exercises. Okay? I want you to check that this action can be rewritten as m by 2 x tilde dot mu x tilde dot mu by e tilde minus e tilde. With an appropriate redefinition of what this tau is. This will be df. It's some right.
So isn't that dt by df tau?
What?
Isn't that d for the e transformation?
This is
df by that's f.
df by
df by deta.
Okay. What I'm saying is that this action here has a reparametrization invariance in it. Okay? That if you change the coordinate, okay? Go on. Why is there DFT now again? Well, this is a rule, a transformation rule, under which the action is embedded. We see why, you see, as we will see in more detail very soon, E is playing the role of a metric on this one-dimensional world. Okay? More precisely, it's playing the role of square root of a metric on this one-dimensional world. And this factor is representing the transformation property of the square root of a metric under a coordinate change.
Yeah, but naively, we treated E as just a variable in the previous step of quantization. So if I were to do this fourth way of quantization myself, I wouldn't have put that df by deta. I would have just done the same kind of thing for x till x and
but then it would have been.
And I wouldn't have got the right answer.
at the moment, all I'm asking you to do is to observe that there is an invariance of the action. If you didn't make this variable change, you would have got a different action, and that doesn't tell you anything. Right? What does tell you something is when you do find an invariance of the action.
But there is no way to see upfront that you have to put that here.
Well, the way to do it is to think about the solution to the equation of motion. E, remember, was square root of minus x mu dot x mu dot. Okay? So now if you make this variable change on x and ask what variable change it induces on E, you get this. Okay, so it is the only consistent.
Or you could rewrite the other action as S as E times read out integral. If we change
right.
so.
Good. So it's the same thing. So E times d tau must be an invariant. That's what he's saying. Okay, good. So however you see it, we've discovered that this action has a reparametrization invariance under a certain change of our variables. Now, this reparametrization invariance, as we talked about right at the beginning, right, is just a change in the labeling of your path. It's a change in the labeling of your path, and therefore there's a gauge symmetry. So, for those of you who are not familiar with the term gauge symmetry, what do I mean? What I mean by this is, gauge symmetry is the word used to describe two apparently inequivalent descriptions of the same physical state. Okay? What's the physical state under consideration? Physical state is the physical solution is the path of the particle in space-time. You make two different parameterizations of the same path, you have different functions, x mu of tau, but it's the same solution. Okay? So if you're dealing with bad variables, or redundant variables, it often happens that two different functions describe the same physical thing. Any situation in which that happens is referred to in physics as a situation enjoying gauge symmetry. Okay? So what we have here is a reparametrization invariance, and the reparametrization invariance is a gauge symmetry of our system. Okay? Now, one way of dealing with systems with gauge symmetry is just to fix a gauge. So it's to say that, well, there are many different functions that describe the same physical state. So let me, in the space of gauge orbits, choose some condition that cuts each gauge orbit exactly once. Choose one function per state. So put a condition on the functions that I'm looking at, such that this condition chooses just exactly one, picks out one function per equivalence orbit. Okay? Now, without thinking too much about whether it's when and whether it's possible, because this is not our main job, we're not here mainly to quantize the particle. Well, let's try to fix gauge. You see, because E changes with F this way, you might think that it's possible, and we won't even investigate that too carefully. Let's try to set E is equal to 1. E was a positive there, right? What was it on a solution? Somebody remember? Square root, yes, that was positive. So let's set E to 1. Okay? That is going to define our gauge choice. Once we've done that action, it's very simple. S is equal to m by 2 x tilde mu dot x tilde mu by 1 minus 1. Now this looks like a lovely action, it's very simple, it's like non-relativistic mechanics. So you might think, well, let me do my quantum mechanics by making this choice of gauge, working in this gauge, and doing my quantization. Okay? So let's see what we get when we do that. What we get is that p mu is equal to mx mu dot, and that h is equal to m p mu plus m squared by 2. 2m. Now, this is the first time that we've done something. You see, this fixing gauge is a slightly fishy thing to do, as we'll discuss in a moment. We've done something fishy and we ended up with a fishy answer. We've ended up with a fishy answer because Now our wave functions in this quantization are function of d variables. And the Hamiltonian is not 0. So the wave functions are actually apparently functions of d plus 1 variables. Oh, this looks bad. Looks wrong, but there's something that's even worse. Let's write this out in detail. This is equal to minus p0 squared plus pi squared plus n squared by 2n. And now you see that the Hamiltonian that we have is a crazy Hamiltonian. This is unbounded from below. All p mu is one Hermitian operators. Square of an Hermitian operator, that's negative. So we've ended up with a crazy system that has no ground state. Okay? So what have we done wrong? What have we done wrong and how can we fix it? Somebody tell me what we've done wrong and how we can fix it. We substituted the gauge into the action. This is very similar to the discussion we had about substituting A0 into 0 into the action. How do we fix it up? See, exactly. What have we missed when we substitute the gauge into the action? What we miss is the equation of motion with respect to varying, with respect to the thing that we substitute. So if we supplement this action with the equation of motion from E, and in that equation of motion then set E equals 1, then we'll be okay. But what was the equation of motion from E? The equation of motion from E was x mu dot the minus divided by 1 because E is 1 minus 1 equals 0, which you can easily see is the set is our good order p u p plus n squared. Okay? So if we just did the naive thing of substituting the gauge into the action, but we remembered to look at the equation of motion from the degree of freedom that we've eliminated and impose that as a constraint, then we get the right answer. Because now we're back to our, I can't remember which is the way of quantizing functions, maybe the first way of quantizing. Okay? So this is a useful thing to keep in mind. You see, this problem was so simple that we could carry out any way we wanted of quantizing each in 5 minutes. We're soon, in fact now, going to turn to a problem in which the quantization is much more complicated. And different ways of quantizing will have different degrees of complexity. So you want to choose the one that is best suited to your problem at hand, and then you have to do it right. Okay? So we have, to summarize, we've had 4 different ways of quantizing the relativistic particle. The first way was to write down the relativistic action. We had d variables, the x mu's. There was Hamiltonian was 0, so it was not a function of tau. There was one constraint which gave us the equation of the effective, the true equation of motion. The second way was the physical way of writing this Lorentz non-invariant action, where we saw we got the same answer. The third way was introducing this auxiliary variable E and doing everything honestly, and we saw we got the same answer. The fourth way was introducing the auxiliary variable E, fixing gauge. If we did things wrong, we got the wrong answer, but if we fixed gauge, did the quantization, then imposed the constraint that came from varying with respect to E, once again we got the right answer. Okay? So now we've got 4 different ways of working, each of which give us the same physics. Okay? So we keep all these in mind when turning to the problem we really want to study, namely how to quantize the motion of relativistic string. Okay. So now questions or comments. This is really good time to ask questions, comments, because we're moving on to the next stage now. We're going to move on to the quantization of strings. So please, discussion before you. Anything you want to discuss about what we talked about now, please do it.
Okay, if there's no question about this stuff, I mean, can I ask something about some of the philosophical things?
Please do. Go ahead.
Okay, if you're saying that string theory is a theory, it's not really a theory in the sense it's not talking about experiments, we're not describing the real world.
Yes.
I mean, what kind of experiments do you think we should be looking at?
Well, you see, what string theory is, in my opinion, this is a big statement, but in my opinion, string theory, when we understand it completely, will turn out to be the correct framework for all consistent thought. Okay? So it's a framework within which consistent calculations can be simulated. Okay? So, within this framework, my prejudices will lie in theory of the real world, but within this framework will lie every calculation you might want. Okay, so if you want to perform the calculation of checking to see whether Yang-Mills theory is a confining theory, it's a calculation that you can fruitfully do in this framework. If you want to find the calculation of computing the viscosity of N equals the fluid that makes up N equals 4 Yang-Mills theory, it's a calculation you can do within this framework. You see, string theories have this eclectic nature about it. String theory techniques have been used in mathematics to significantly impact entire branches of mathematics. For instance, my colleague Indranil Biswas once estimated that if you look at the top algebraic geometry journal and ask which of the papers that are written there today, what fraction of the papers written there today could not have been written had string theory not existed, the answer would be about 30%. That's a big impact of a field. Okay? People who are trying to study the experiments at RIC today, heavy ion collisions, in order to model what's going on, are using crucial inputs from string theory. Okay? People who, this is much smaller, but to be such they have an eminent condensed matter theorist and trying to understand the dynamics about quantum phase transitions in real life systems, is using calculations from string theory to help. So, at the very least, that's what string theory is. It's a calculational framework of great versatility. Okay? That can be brought to bear on many different physical systems. Okay. That is at the level at which it has impacted experiment today. Will it do more? For that, we don't know. As all of you know, this big experiment, the LHC is out. We're going to get results whenever it does. Let's say in 3 years we'll know something about what's going on. If it turns out that supersymmetry is a feature of the real world, then even though supersymmetry is not a prediction, it's not a low energy supersymmetry, it's not a necessary prediction of string theory. No, the study of string theory is a place where the idea of supersymmetry emerged. First supersymmetric action was the one written down over a chain string. So, how these ideas are going to impact experiment is hard to say at the moment. The most direct way in which it might is if you find the right implementation of the real world with the string theory. But even without that, the study of string theory has already had a significant impact on the study of physics in various different fields. And perhaps even more so in the study of mathematics. And in my opinion, is likely to just keep having more. Because it's the most powerful, in my opinion, calculational technique that human beings have hit upon. This is my take. Other people would say different things. This is good. Okay. Other questions on it?
You put the value for E as 1 in this focus.
Right.
So, but would it come out and then we finally had to add in the constraint equation, which is the equation. Is it the same thing as putting the determinant of the here beta of variation that goes to 0?
I didn't understand. Putting what?
We have this F beta in the transformation of beta. Right? Now, under a variation of tau, F beta changes in some particular fashion.
Right.
And saying that should be put in as a Dirac delta function into your action.
No, I don't. If I understand you right, you're thinking of sort of fuzzy Popov kind of fixing. And the variations of gauge conditions help determine the measure of the path. We've not reached such subtle issues yet. We didn't. That's like a small addition to what's going on. This is much more basic. So I don't. My answer is I don't think that's the same issue. Okay.
Choosing a particular value of E is basically cropping up from choosing a particular form for F. Right?
Yes, you're fixing your reparameter. Exactly. You choose F. In fact, you choose F so that df by d tau is 1 over d. That says d tau is 1. Nothing. Okay? Now, E is basically it's for the consistent. If this were our main job, we would do a very thorough analysis when such a choice is possible. Are there further redundancies? As you will see, when we move to the worksheet of the string, which is our main study of interest, we will do a very thorough analysis of any gauge fixing. But for now, we just don't want to get into this this thing for the next 2 lectures, so I'm not going to worry too much about when it's possible and so on. There's more subtle issues we'll deal with in the system of interest. Okay, the justification of the system works. The answer, you get the right answer, you must have done it right. So, or mistakes are cancelled, that's fine. Okay. Okay, great. Other questions or comments? Otherwise, we turn to study the string. Good. So let's turn to our study of string theory. Oh, something I should have said, of course, is that the equation that we kept encountering, this d squared minus d squared plus m squared upon psi equals 0, of course, the famous equation for the quantum mechanics of a relativistic scalar particle is Klein-Bordern function. Okay, that's a famous thing, of course. It's the correct way to study scalar fields. We get this just by quantizing the relativistic particle, as you would expect. Okay. Fine. Now, what we're going to try to do now is to quantize the motion of what's called a bosonic string. What is the word bosonic mean? Well, it means that the result of this quantization will give us particles in space-time that are only bosonic. Actually, on a more technical level, it means that on the word sheet, you'll see what that means. We'll only deal with bosons. We'll come back. We'll come back to improving this. We want to measure this real world for instance. It's made up a lot of fermions. Fermions are very interesting. But we're doing this in round 1. Round 1, you ignore technical complications to try to quantize a bosonic string. Okay. So, how do we go about this? So, what's a string? So, string is an object whose history in space-time is 2-dimensional. Okay, it's an object with a loop, but also moves in time. So you can think of the world volume of the string as a little cylinder in space-time. Okay, and what we want to do is write down an action for the motion of the string. So an action that depends on the world volume, cylindrical world volume of the string. Okay, so first let's hit upon some parameters. Let's choose sigma as one of the parameters. Sigma, of course, as always, we will never say much about the parameters, except for this one statement. Sigma will be chosen to be to lie between 0 and 2 pi. And every field will be periodic in sigma. What we're doing by saying this is enforcing the topology of our surfaces, enforcing that we're studying cylinders. So sigma is one of our variables. Everything's periodic. Sigma from 0 to 2 pi. The second variable is tau. We say nothing is, tau goes from minus infinity to infinity, nothing is periodic at tau.
You are talking only about closed strings now?
At the moment, yes. Okay. So, good. So, those are our parameters. What are our variables? Our variables are x mu of sigma. Okay. Once again, this is physically redundant. These variables are physically redundant, of course. Okay? Because you could use one of the coordinates in space in some sense. You can use time for tau and some other functional spatial coordinates for sigma. So actually, the real number of variables is d minus 2. Okay? But we're not going to worry about that. We're not just going to carry out the formal quantization procedure, do it right, and get the answer out of it. Understand that we actually have a mean. That should be the result. Okay, so these are variables. Next question, what is the action? Now, when we study the motion of particles, in order to choose the action, well, we chose as the action a geometric quantity. That is a good thing to do because it ensured that our action was reparametrization. It's purely geometrical, so it doesn't count parameters. Let's try to do the same thing for a string. We also have geometric quantity that depends on a 2-dimensional world sheet. Well, what quantities do we have in our hand? We could write down many, but let's choose the simplest one, the analog of the length of the line. The analog of that is the area of this 2-dimensional surface. Okay? So let's try to write down an expression for the area of this 2-dimensional surface. First, once again, let's do it first in Euclidean space, then we figure out the right minus signs to go to Minkowski space. Okay? So how do we get an area? See, suppose we've got some world sheet, and we vary sigma a little bit, we move in this direction of the worksheet. We vary tau a little bit, we move in this direction of the worksheet. Okay. This vector, what was it? Well, it was delta sigma times dx mu by d sigma. This infinitesimal vector was delta tau times dx mu by d tau. Okay? Now, in this little variation, what is the area that we swept? Well, this is an elementary question. It's an elementary question which you could ask a high school student, and he would think and say, well, it's a parallelogram. It's a parallelogram generated by two vectors. So the area is A, B times sin theta. And theta is the angle. A is the length of the first vector, B is the length of the second vector, sin is theta is the angle. Okay? But, we want to address this in slightly more, write this in a more invariant way. So it would be useful for us to write this as square root of A squared, B squared, 1 minus cos squared. Why is that useful? It's useful because each of these expressions can now be written as a dot product. This is A dot A, this is B dot B, and this is A dot B whole thing squared. Okay, so the area is square root of A dot A into B dot B minus A dot B, the whole thing squared. So this quantity, the quantity under the square root, is simply the determinant of A dot A, B dot B, A dot B, A dot B. Okay? And now let's remember what A and B were. A and B were these quantities. Okay? Dot means contraction of these indices. So what we concluded is that the area is square root of determinant del x mu, del alpha x mu, del theta x mu. Is it over?
It's almost 5 minutes.
5 minutes. Okay, so you understand what this matrix is. It's a matrix whose indices are alpha and beta. It's a 2 cross 2 matrix, and we've written this down in this nice compact way. Fine. Now, we were, as we discussed, we will be interested in strings that are moving in this nice tag-like fashion. Okay? Therefore, one of the two of A and B will be a time-like vector. So, for instance, if we chose things that were orthogonal, this quantity would be negative. So clearly, if we want to be working with, Minkowski situation, we want the minus sign there. And so finally, we choose the action to be t now before the sign minus t. So